line is, like I said, on work on an inclined plane, and the cross product of two vectors. Okay, so basic physics concept. I'm not sure like how in depth you've gone with physics types things in your science classes, but if we say that someone weighs 150 pounds, gravity is included. This is a force. Okay, so the weight is a force, but the mass is not. I'm going to try to give you guys everything in terms of forces. Okay, so I'm going to give you weights instead of making you do mass times gravity and so on. Okay, so like I said, I'm going to kind of dumb it down a little bit for pre-calc, but if you guys go into physics, you'll at least have seen this before. Okay, so anyway, it says the vector F pointed straight down shows the weight of a box. So I drew this beautiful picture for you guys on there. Whatever weight of the box you have, it's going to go straight down, just like gravity, straight down, right? You're not going to have the weight like pushing in this direction or anything. It's going straight towards the ground. All right, so one thing that you're going to need to do in physics is you're going to have to draw these diagrams a lot. Okay, so the weight vector is then broken into two components. One of these is going to be perpendicular to the ramp, and one is going to be parallel to the ramp. Okay, so basically if you have this big ramp, maybe I'll do it on this one, you're going to have one force that's headed straight down, and you can make it as big as you want. It can go like all the way down here if you want. It doesn't matter. Right, and then one force is going to be parallel to the ramp, and one is going to be perpendicular to the ramp. Okay, so you're always getting a little right triangle. Do you guys see how I drew that in? So the key is drawing this very first one, which is the weight of the box. Okay, it says the one parallel to the ramp gives the force needed to keep the weight from sliding down. So if you just basically had a box, think about like a U-Haul ramp. Your box is sitting on the ramp. If it's really, really heavy, it's going to start sliding down the ramp, right? If it's not really heavy, it might just stay right there. Okay, so it's saying what kind of weight do you have that will keep it just staying right there? Natalie, put the computer away. All right, so I asked Mr. Crowley what he prefers. Do you prefer using an F? Do you want to use a W? He says he usually uses a little w. Okay, I used force, so you guys remember in the equation, it's the force. It doesn't matter what you use. All right, so number one, it says a cargo plane is being loaded. The ramp is 3 meters high with an incline of 20 degrees. Okay, so we have all those drawn in. The box weighs 200 pounds, so 200 is going to be the force that is straight down. Okay, that's a weight. It includes gravity. It goes straight down. And the worker plans on sliding it up the ramp. What force is required to keep the box stationary? So basically you're finding this number right here, the force that is parallel to the ramp. That's what we want to find. Okay, and it's kind of cool because it works out that this 20 degrees that you have right here, it's also right here. Okay, do you guys see where I drew it? At the very top of that triangle. Okay, and the reason is because you have parallel lines. I mean, you can draw on your parallel lines. You could draw in transversals and so on, but those end up being exactly the same, okay? So we have 20 degrees here. So we have a triangle. Oops, that's not a very good triangle. We have a triangle where we know that we have 20 degrees and 200 here, and we're asking, what is this number? Okay, would we be able to solve that right triangle? Yeah, you guys can solve it using SOHCAHTOA. Always resort back to our SOHCAHTOA, right? If we wanted SOHCAHTOA, we want the opposite and we have hypotenuse, so we would set it up as sine. So what that question mark ends up being is it's going to be sine of 20 degrees equals whatever that question mark is, opposite over hypotenuse. Okay, that's why in the diagram I wrote F sine of theta. Do you guys see that? So if you just have that memorized, you will always know the force required to keep it from sliding down is going to end up being F sine of theta. So our original force, the weight was 200. We have sine of 20 degrees. And so we find that. So go ahead and get your calculators out. Make sure you're in degree mode because we have 20 degrees. All right, so we end up getting 68.404, like that. All right, now the units are really weird. The units, it's a force, right? So, well, the units aren't weird on this one. It's going to be weird on work. The units for this are going to be pounds. Okay, so whatever your initial force was in, it's going to be the same. We're getting ready to talk about something called foot-pounds. I was thinking ahead. Isn't that fun, foot-pounds? All right, so the next one. So it says, we know that if someone's pushing a box, it matters how heavy the box is, right? The force of the box. It also matters how long the ramp is, so the distance. Okay, so I'm super pregnant. If I'm going to push a 200-pound box, I can probably push it a couple inches, 6 inches. But if I have to push it like 20 feet, there's no way that I could do it. I would be dying. Okay, so I'm definitely going to have to call in some reinforcements. Does this make sense? So just kind of nudging it and pushing it for just a second, that doesn't take a lot of work. But if I'm going to push it for a really long distance, really far, do you guys understand that that takes a lot more work? Okay, so there's something related to force, which is called work. Okay, and work ends up just being force times distance. Okay, but we use this equation when it's a flat surface. So only when we're like pushing along the ground, right? But if I'm pushing something up a ramp, well, then it really matters, because what if the ramp is super steep? Then it's going to be even harder to push. Does that make sense? Okay, so we have to consider how the ramp is affecting it. And this is the equation that I told you that we would use today. So it says, therefore, if I'm pushing 200 pounds, a 200-pound box along 6 inches or half a foot, your work ends up being, it's either, here's the units, foot-pounds. So we're going to have 200 times 1/2. It ends up being 100 foot-pounds. 200 feet, or not 200 feet, 200 pounds multiplied by 1/2 foot equals something in foot-pounds. All right, so there's really strange units for work. So if you push the box 20 feet, so if I only push it, or if I push the 200-pound box 20 feet, the work is a lot more. It's 4,000 foot-pounds. Okay, so it ends up being like 40 times what the other one was. So if we move this box up the ramp, you end up using the force that's perpendicular to the ramp as the new force in the work equation. It's basically like you're taking this like plane and you're pretending that it's a flat surface, like you're rotating it. Do you guys understand what I'm saying? It's like if I take this and I rotate it so it is flat, right? But the force that I'm using is the one that's straight perpendicular with that. It's the one that's perpendicular. So what's that? That's the F cosine of theta. Do you guys see what I'm saying? So I don't use like just the weight of the box anymore. I use F cosine of theta for my weight. Okay, so all you really need to know is that the work on an inclined plane or inclined plane is going to be work equals FD cosine theta. Okay, if you know that, you're golden. That's all I'm going to test you on. There could be lots of fun physics problems where, you know, there's friction involved. We're not doing anything with friction. There could be things where someone's pulling on a rope one direction and someone's pulling another direction, and does the box move up the ramp? I mean, there's crazy stuff in physics. You can take physics and learn about all that. All right, so number one, it says a 2,000-pound car is parked on a street and it makes an angle of 12 degrees with horizontal. Find the magnitude of the force required to keep the car from rolling down the hill. So I think I do ask you on your homework to draw the picture, so we'll go ahead and draw the picture. Okay, so our hill is 12 degrees. We have some kind of car. You can draw a pretty car if you want. I'm just going to draw a little box. Maybe I'll put some wheels on it. I'm feeling crazy. Yeah. You can draw a much better car than I can, I'm sure. Yeah, I am. All right, and then we always have that force headed straight down. And that's going to be the weight of the box, which is, or the weight of the car, which is 2,000 pounds. So can you guys see that? That's 2,000. It's kind of tiny. 2,000. All right, and then we draw the little things that are parallel to the ramp and perpendicular to the ramp. So go backwards. Go up along the ramp. See how that's like parallel? I'm trying to draw it parallel. And then straight down. Okay, and that creates the triangle. It's a little hard to draw the triangle at first. It will take some practice. So if you remember, this is going to be F sine of theta. So it's going to be whatever 2,000 times sine of 12 is. And this other one is going to be F cosine theta, which is 2,000 cosine of 12. Okay, that's the new force in our equation. That's the F cosine of theta. Okay, we've already taken care of that. So it says find the magnitude of force required to keep it from rolling down the hill. So you're keeping it, like just like we talked about the box stationary or the car stationary or whatever. Which one is that? Is that F sine theta or F cosine theta? F sine theta, right? So we're going to do 2,000 sine of 12. So we end up getting 415.823. Our units would be the same. It's force, right? So if it was in pounds originally, it's going to be pounds here. So when it says find the force perpendicular to the street, well, that's going to be the other one. That's the F cosine of theta. So it's going to be 2,000 cosine of 12 degrees, which when I put that in, I get 1,956.295 pounds pushing down on that street. All right, and then the next question says, well, find the work done in moving the car up the hill a certain distance. Okay, that's what's important in the work equation. You need to know how far you're moving it. Okay, so the work equation is always FD cosine theta. We already did the F cosine of theta. We did that. Okay. But we'll go ahead and plug it all in. So we have, what was it, 2,000 pounds? 1 ton? Yeah, 2,000 pound car. We're moving at 100 feet at an angle of 12 degrees. So I'm taking that last answer that I had and I'm just multiplying by 100. Okay, now we think about our units. So the distance was in feet. And the force was in pounds, so this is where we have that lovely unit of foot-pounds. So it's not foot divided by pounds, it's just foot times pounds. Make sense? Easy enough. Do you guys think you can handle those 3 parts, A, B, C? It's really not that bad. Those are the formulas you need to know. All right, to pay for college, Emerson works in the summer for UPS. My father-in-law is a big UPS guy, so. All right, suppose his, I don't know what this is saying, suppose he is pushing a cart full of packages up a ramp 10 feet long at an incline of 15 degrees. So let's try drawing the picture again. The cart weighs 100 pounds. So that's the force that's going straight down. We have a parallel and a perpendicular. Find the work done in pushing the cart all of the way up the ramp. Oh, I don't know what is up with this question. I need to learn grammar. All right, so you can draw all the different things. That remember, this is 15 degrees as well. You can say, okay, this one going straight down is 100, and you can always get it with SOHCAHTOA if you get confused. So as long as you have the picture, you can always use SOHCAHTOA. But remember, all we're doing for work is we're doing FD cosine of theta. And we have all the information that we need. We have the force, right, the weight of the ramp, or not the ramp, the cart, so 100 pounds. The distance that we're moving it, 10 feet. And the angle, which is 15 degrees. So we have everything. So we plug it in. So you get 965.926. And our units would be, again, foot-pounds. It's not always foot-pounds. All right, so the same thing happens even if you have like a, like this one is about a towing truck, a tow truck. So the cable that you're pulling it along is now 50 degrees with the road. Okay, it's treated just like an inclined plane. It's treated just like a hill. That's, I mean, I can draw out the picture. It's kind of complicated, but it's the same as when you have a tow truck and you're pulling at a certain angle, treat it just the same way. Okay, the tension in the cable is 1,600 newtons. That is a force. How much work does the truck do when the car is towed 1.5 kilometers? Now notice how it's saying write your answers to the nearest Newton meter. What's wrong with the units in my problem? Do I have newtons? Yeah. Do I have meters? I have kilometers. So I'm going to do 1.5 kilometers equals how many meters? Yes, good, 1,500. Right. There are 1,000 meters in every kilometer. But otherwise, it's exactly the same. So we say the work equals the force times the distance times cosine of theta. So the angle that you're pulling, like the cable, is kind of like you're pulling it up a hill at that angle. So it's going to be 50 degrees. So we have 1,600. The distance is 1,500. And then cosine of 50 degrees. I tried to find a nice picture of like a tow truck where I could draw on it, but Google Images failed me. All right, and your units are Newton meters. Anybody know what else those are called? Anybody in physics right now? Newton meters?
Joules.
Yeah, it's joules.
We just keep like joules.
So you can just do a J for joules if you want. I'm fine if you keep it as Newton meters. It doesn't matter. It's just another name for it. All right, was that the last one? Oh, okay. So that's the last one with the inclined plane. All right, so the last thing we're going to learn about is something called a cross product. So we have been dealing with vectors in 2 dimensions, right? It's on like a flat page, like a 10 by 10 grid, and we can draw them out very easily. Okay, but vectors aren't always 2 dimensions. Sometimes they're 3 dimensions. All right, so I'm not going to have you draw these. I had you draw these when you were in Algebra 2, like a point in 3 space. Do you guys remember doing that? Like where I said, draw this point, -1, 2, 5. And then you had to draw the x-axis, the y-axis, the z-axis, and you had to go back -1, over 2, up 5. Do you guys remember that? And some of you guys like totally panicked. Well, it's the same thing for vectors. You're still doing kind of you're creating a box shape as you do this. You guys don't quite understand it, I know. So you get that box shape, and it's going to the back corner. Does that make sense? I'm not going to make you draw these. Don't worry about it. You don't have to draw it. Some of you are sad because you like drawing. Julie looks so sad that I said you weren't going to have any art. All right. But anyway, if we want to find vectors that are perpendicular to 2 other vectors. Okay, so think about this. Corner of the classroom is a perfect example. So along the wall, you have a certain vector. Along the other wall, you have a certain vector. There are vectors that are perpendicular to both, right? A vector that goes up like that. Does it make sense? Did you get it? Even if the vectors are really close together, you could have a vector that would be perpendicular to both. It'd be coming up off the page. It's kind of hard for me to draw. I should have drawn that better. Like imagine a book. Let's say I have a book that's like open. I'm not drawing this very well. Right? This vector is perpendicular to both of these vectors. Do you guys see? There's 90 degrees. Like, do you understand this? Some of you guys are not good with thinking in 3 dimensions. I know that you've had trouble drawing these things in the past. Anyway, so we want to find this. We want to find what a vector that would be perpendicular to 2 other vectors. And we do this using something called the cross product. Okay, so it's pretty easy to find as long as you remember some basic facts about matrices. Do you guys remember your matrices? Do you remember how to find the determinant of a matrix? It deals with the downwards diagonal and the upwards diagonal. All you do is you do 4 times 3 minus 5 times 2. So you get 12 minus 10, which is 2. Can we handle that? Downwards diagonal multiplied. And then upwards diagonal multiplied. Subtract the 2. Jimmy Neutron. Yeah. All right, so downwards diagonal, -16. Upwards diagonal, I'm subtracting it out, -5. My total answer, -21. Does it make sense? So the formula, if you want it, is AD minus BC. Downwards diagonal minus upwards. So you always do down minus up. Can you at least remember that from matrices? That's all we need. We're going to do more with matrices later in the year. I know you're excited, but we'll revisit. Okay, so we didn't talk about this in Algebra 2, but you could use something called cofactors. Do you guys remember doing the really long like lattice method to find a big determinant? Okay, you could have also used something called cofactors. I didn't use cofactors. I did the really long way. All right, so here's what we're going to do. And it's probably best if there's a formula here. it will make more sense probably if I just write it for these ones, okay? So what we do is if we're doing A cross B, we put both of them in one big matrix. But the top row is IJK. Do you guys remember IJK? That's like the, yeah. That's like, I could have also written this vector as negative I plus 0j plus 3k. Do you guys remember?
No.
Like it's the other form of writing matrix or writing vectors. I usually use the little pointy things. Okay. So I'm going to have A1, A2, A3. So this is going to be the first vector. I'm going to have negative 1, 0, 3. Do you guys see that's the first vector? Negative 1, comma 0, comma 3. And the second vector was 1, 2, 4. We're still going to get a number in front of I, a number in front of j, and a number in front of k. But I want you to remember that the middle thing is negative. The j is going to be the opposite of the determinant that you get. So don't forget that negative. All right, and what we do is we use these things called cofactors. So it's really not hard. Okay, watch what I'm crossing out. I'm only going to cross them out really quickly. So if I want the number that goes with I cross out the I row and the I column. This is what's left. I put those numbers in here. Does that make sense? Okay, I'm going to delete it though, because I want to keep those numbers. So 0, 3, 2, 4 here. All right, for the next determinant, what do you think we do for j? Cross out the j row, cross out the j column. What numbers are left? Negative 1, 3, 1, 4. And then for the k one, again, cross out the k row, cross out the k column. So we have negative 1, 0, 1, 2. Does that make sense? Can we find the determinants? 0 minus 6 is negative 2i. Minus negative 4 minus 3 is negative 7j. But still, remember I have that negative. You don't want to forget that negative. It'll mess it up.
Wait, where did the negative 2 come from? Why is it negative 2?
Oh, because I did 4. 4 minus 6. 0 minus 6. Thank you. Negative 6. I don't know who blurted it out first. No. All right, and then the next one I have negative 2 minus 0.
Where'd the subtraction sign come from?
The subtraction sign is in the formula. It's right here. It's a minus in front of the j. All right, and then I have negative 2 minus 0 is going to be negative 2. Okay, so your final answer is negative 6i plus 7j minus 2k. So if you don't like that form of the vector, what is it? It's negative 6 comma 7 comma negative 2. Same thing. That is the vector that's perpendicular to both of those. Make sense? Think you can handle that? It's not very hard. I think you got it. All right, is that the last problem? I think that is. Yeah.
What do you say?
Hang on.